Okay, so we will now find some nice properties about those P and how we can relate to other things. So we define first the defect of a prime. So suppose we have a pair of elliptic curves and a prime P, and they're anomalous. I just write it like this, and I hope it's clear that they, yeah, no, I maybe, no, this should be good like this. Okay, so then this is kind of a bit of a definition, but also a bit of a lemma or proposition that we can actually define it like that. So if we consider the FP squared points and consider the two power torsion. So all the torsion points that are 2 to the something torsion points. And if E over FP squared has full 2 to the A torsion, so where A is just a positive integer, but not full 2 to the A plus 1 torsion, and E prime of FP squared has full 2 to the B torsion. I think I will formulate in a way that this is only the definition, and I will write something else next, but not full 2 to the B plus 1 torsion. Then we call AB the defect of the prime. So with the example from the beginning, it's not on the board anymore, we could have looked at the FP squared points and the of E and the FP squared points of E prime, and then consider the 2 torsion, the 4 torsion, the 8 torsion, and so on. And then, since the groups are finite, there's one point where it stops. So at one point, which can already be 0, so only full 1 torsion, at one point it stops where it has full 2 to the something torsion, but not 2 to the something plus 1 torsion. And this will happen for both curves. And then we call A, B the defect of the prime. Now the question is, of course, are A and B somehow related? Does this maybe happen at the same level? Well, but then it could also happen that they are still isomorphic, so this is maybe not very likely. Or does it happen totally independent from each other? And for some intuition, we define isogeny volcanoes. The people who attended Fabien's talks 2 weeks ago or 3 weeks ago have already heard of it. So what's an isogeny volcano? Well, maybe first the intuitive definition. We are over a finite field, let's say Fp, and then we consider all the elliptic curves over this finite field. We could also identify them with their J invariants, because this is a one-to-one correspondence. But just consider the elliptic curves. You have a puzzle on the table, and the elliptic curves are the points. And then you relate them if there's an isogeny between them. Yeah, well, when we defined isogenies, it was a map from something to something. But the fact is, if you have a map from here to here, that's an isogeny. There's also one in the other direction, but that's a black box. You don't need to know why. So we connect all the elliptic curves where we have an isogeny. And since we're interested in two isogenies, we look at the two isogeny volcano, where we only connect the curves if they have a two isogeny between them. But we give the definition for general L. An L volcano V is a connected undirected graph whose vertices are partitioned into one or more levels. Such that the first one is a regular graph of degree at most 2. I will write it in a second. I will give an example in a second. For I positive, each vertex in one of the levels, that's not the first one, has exactly one neighbor above it. One and each vertex except in the last one has degree L plus 1. And maybe also in the, not in the first one. I think we have to put greater than 0. Yeah, but I will write draw a picture, so that will be more clear. An isogeny volcano is basically a circle with trees. We have trees here. That go until some level. And for L equal to 2, we have that every point, every vertex has 2 neighbors below and 1 neighbor above. And for the general L, it's L below and 1 above. So this. Here are some trees. Well, this means this is a tree, so we only have 1 here. And all those vertices are elliptic curves. And if we consider all elliptic curves for one fixed finite field, it can happen that this is one volcano or more volcanoes, maybe a small one, a large one. But the connected components are always volcanoes that look like this. And I think we call this the crater. So we can actually use volcano words. So this volcano theory is used to, well, for calculations and deriving stuff that's maybe not so easy in the elliptic curves world, but maybe easy in the graph world. And one thing that we can get from the whole volcano stuff is the following. That if we have anomalous primes, and we consider all torsion of some power L. So this means the L torsion and the L squared torsion and the L cubed torsion, all the L to something torsion points. And the theorem says that if this is of this form, then here we get either that we have here one power less and here one more, or the other way around. Which was also one of the questions when I wrote down the points of those elliptic curves over F17 and F17 squared, because there we had exactly this case, and now this theorem tells us, maybe we should call it theorem. This theorem tells us that this will always be the case, that if they differ, then they differ in a way that it's just one power moved to one other side. So you see here the sizes of the groups are still the same, because here we have L to the U, L to the V, and the difference from here to here is just that here we have an L more here, and here we have an L more here. And what does it have to do with the defect? Okay, we go back to one example of the isogeny volcano. Well, this is, I will not formulate it as a theorem. This is more in a probabilistic view. When you calculate this 1 over 30, then you have infinite sums, and you need proportions of primes, and then you can also filter them by the defect they have, where you don't really need the property that you know exactly when is the defect what, but you only need to know it probabilistically, basically, because you run over everything and look at the distribution. And the interesting thing is that basically the defect of a prime is where in the volcano the elliptic curves lie. So when can two elliptic curves be anomalous? When they have an isogeny. So this means they are here next to each other. Next to each other means, for example, one is here, maybe one is here or here. They cannot be on the same level of this VI, and they can only be on levels that differ by 1. So for example, if E is here and E prime is here, then this is on level 1. this is on level 2. And if they are anomalous, then the defect of the prime, remember this is all over Fp, then the defect is 1, 2. And this also means something else. This means if we consider the defect of a prime, then it's always of the form is always of this form, because they can only differ by 1, because they lie on different levels on the volcano, which can only be 1 apart, because this elliptic curve and this elliptic curve are not 2 isogenous, because otherwise there would be a line between them. Yeah? Let me think about that. This would mean well, this would just not fit in our definition, because then they would have to have full 1/2 torsion, because then A would be negative. But let me think if it's possible that they're anomalous. I think this can just not happen because they are on the same level. Yeah, but this is of course a circle argument, circle, because I argue by this that it looks like this. I think it cannot happen. I'm not sure right now. So the defect is always of the form m plus 1 or m plus 1m. And in the case of this theorem with the 1/30, where we have this maximal Galois image, then actually all the m's can appear. Let's call this star. So in the setting of theorem star, all m can appear. So the next question would actually be, so let's look at what conditions do we have here. We have here this 2 isogeny, but if we have another isogeny that's not a 2 isogeny, then we had another theorem that told us that everything's fine. And the other condition is the image of their 2-adic Galois representation is as large as possible. So it would now be interesting to find out what happens if it's not as large as possible, and if it's smaller. Yeah, and then in that case, we can basically take this image of the Galois representation and go to the LMFDB, to the database of elliptic curves, and look at what first we go to another database, to the RZB database. It's a database where people wrote down all the possible 2-adic Galois images of this kind. Then we could pick one curve that has this Galois representation, go to the LMFDB, and look at the isogeny volcano. It's actually usually, I think, actually drawn there. So usually it's maybe a bit smaller. But they sometimes they have it drawn there, and you can see what elliptic curves do exist that are isogynous to those. You could actually try to, by hand, find all the anomalous primes in the different cases where the Galois image is not as large as possible. And the interesting thing also, and well, the thing that makes it possible to compute is, or at least possible in the way that it's maybe computed, is that in that case, M, not all M can appear. I'm not sure if M is actually bounded, maybe by something like 10 or something like that. But I think in all the cases that I've seen, M is not too big, so you could just kind of go through the volcano or go through the torsion points and look at what point the torsion points get smaller. And so maybe this will be something that comes out maybe 2024 or something like that, with the same theorem, but without the condition of the two-adic Galois representation, and then probably some different cases where in different cases the condition is different. Yeah. Okay, this actually, yeah? What? U and V are basically the defect, because it comes from here. It says that the point when the two torsion, or here the L torsion points, are not the same anymore. The point is exactly, not the point. Then the groups look like this, that they're almost the same, but one power goes to the other side. Yeah. And L is our 2 here, but just more general. Okay, so this was everything I wanted to cover today. Let me talk a bit more about the exam. Maybe I will clean the board. So the exam will be, I will clean the board first. We will have 2 dates, March 1st and March 6th. And I will probably pick dates in the afternoon. And I will distribute them. I will put online a list of topics that we covered. Well, basically it's the book, and then the paper on, or the survey paper on complex multiplication. And I will also put the paper online that I talked about today. But I will still give you some topics to have a good overview, what you all have to cover. And yeah, the course is called Hands-On, so I want you to be able to compute things. But of course, in the oral, so it's an oral exam, and I think 20 minutes. Of course, you will not be able to do very long calculations in the oral exam, but I want you to be able to explain how the calculation would be. So you should make me believe that that you are capable of doing calculations. And I will also give a list of calculations that you should be able to do. I will put them in StudIP. Are there questions? I would say duplication formula, yes, but that's maybe the border. So you don't have to, well, duplication formula is really easy, right? So it's just two polynomials in, yeah. And, but you also have to be able to do Lutzner-Galois calculations, to calculate the images of Galois representations. And there, of course, only for 2 and 3 maybe, and everything larger is impossible. Also finite points for maybe p up to 13. Yeah, a bit of calculations should be possible. And I also thought about the possibility of taking a sheet of notes with you, but yeah, that's probably, it's better for you if you were not allowed to do that, because then you would just have to, look at the paper all the time and look, yeah, I think this would be not so good, yeah. Okay, more questions? Well, then thank you very much for your attention for this whole semester. I'm really very excited that so many people were here. So usually in master courses there are like maybe 2 PhD students and 1 master students, and yeah, I really like it that you were so many people. Okay, and see you on March 1st and March 6th.